Hello everybody, myself Prasanta Mukhopadhyay, faculty member, Electrical Engineering Department, Greater Kolkata College of Engineering and Management. So in this class of electric machine 2, we have in the last class we have started a new unit that is single phase induction motor, and in the last sessions we have discussed single phase induction motor, why it is not self-starting, its construction and how it works, and so why it is not self-starting. In support of that there are two theories, double revolving field theory and cross field theory. But I told you in the last class that is both the theory yields more or less same result, and but double revolving field theory is very much is in discussions, and we in our curriculum also we will it is noted that the double revolving field theory is there, and we have discussed double revolving field theory today. So we'll start a new topic that is equivalent circuit of single phase induction motor. So let us start how the equivalent circuit of the single phase induction motor can be drawn. So equivalent circuit of a single phase induction motor can be developed on the basis of two revolving field theory, and to develop the equivalent circuit it is necessary to consider standstill or block rotor conditions. Okay, so actually the motor with a block rotor merely acts like a transformer which is secondary short circuited, and its equivalent circuit that is shown here in this figure. Let's this EM is the EMF induced in the stator winding. Okay, and motor now be viewed from the point of view of the two revolving field theory. The two flux components induce EMF, say EMF F and EMF B, that is the forward flux, and this is the backward flux in the respective rotor and stator winding. Since at standstill the two oppositely rotating fields are of same strength, the magnetizing and the rotor impedances are divided into two equal halves connected in series, and that is shown here. Okay, this is two magnetizing and say magnetizing and rotor impedances are divided into two equal half, clear, in series. So that is shown here. Okay, so if you compare it with this, you'll just see this is divided. Actually this is divided in two part, this is also in two part, this is also in two part, and connected in series. This will be like this. Okay, so basically actually this is on the this equivalent circuit of the single phase induction motor at standstill on the basis of two revolving field theory. Now when the rotor runs at speed n with respect to the forward field, the slip is S with respect to forward field, and 2 minus S with respect to backward field. That we have discussed in the double revolving field theory discussions, and in that case the equivalent circuit will be like this. Okay, clear? This is for forward and this is for backward. See, this is at slip S forward field, and this is at slip 2 minus S. Okay, so this is equivalent circuit for single phase induction motor in respect of, so actually under normal operating conditions. So okay, if the core losses are neglected, the equivalent circuit is modified, and it is shown here. If we neglect this core loss, okay, so this equivalent circuit will be modified like this. So this component, actually this resistance represents the core loss component, and if we neglect it, so this branch will be not shown. So as a result it will be like this. Okay, so this is the approximate equivalent circuit of a single phase induction motor under normal operating conditions. Clear? So this is in a very specific and in a short fashion to represent the equivalent circuit of a single phase induction motor starting from its block rotor conditions to normal running conditions. Okay, so I hope you will understand it, and for much more details you can contact your textbook, any textbook which we have given. For further reading you can consult, and if you have any queries also you can contact me. We will explain. Okay, but this is in a nutshell, that is the how equivalent circuit is developed for a single phase induction motor starting from its block rotor condition to normal running condition on the basis of double revolving field theory. Okay, so now we'll start our new another topic, that is starting methods of single phase induction motors. Say single phase induction motor with main stator winding has no inherent starting torque, and since main winding introduces only stationary pulsating air gap flux wave, and for the development of the starting torque, rotating air gap field at starting must be introduced, and several methods which have been developed for the starting of a single phase induction motor may be classified as follows. So once again I am telling you, a single phase induction motor with main stator winding has no inherent starting torque, that we have discussed, and since main winding introduces only stationary pulsating air gap flux wave, so for the development of starting torque, rotating air gap field at starting must be introduced. So there are several methods which are being developed for starting of single phase induction motor, and that can be classified as split phase starting, shaded pole starting, repulsion motor starting, and reluctant starting. Okay, once again I am telling, split phase starting, shaded pole starting, repulsion motor starting, and reluctant starting. Clear? So a single phase induction motor is commonly known by the method employed for its starting. Okay, so what type of motor this single phase motor is, induction motor is, so that is being known by their starting methods. Okay, so selection of a suitable induction motor and choice of its starting method depends upon several factors. So first one is torque speed characteristics of the load from standstill to the normal operating speed. This is another one, say, choice factor. Torque speed characteristics of load from standstill to normal operating speed. Okay, and the duty cycle, and thirdly the starting and running line current limitation as imposed by the supply authorities. Okay, so these are the three criteria: torque speed characteristics of load from standstill to normal operating speed, duty cycle, and starting and running line current limitations as imposed by the supply authorities. Okay, so these are the introduction of starting methods of single phase induction motors. Now we'll discuss one after another the different starting methods. So let's start with split phase starting. Basically, split phase starting, single phase induction motor actually employing this split phase starting methods. So by splitting, with the stator windings, all the split phase motors have two stator windings, a main or a running winding, and an auxiliary or static winding. Here, all the split phase motors have two stator windings. One is the main, that is also known as a running winding, and another is the auxiliary, that is also known as the starting winding. When we have discussed in the last class the constructional features, we have discussed where in the stator slot, which way the auxiliary winding and the running winding or main winding has been placed and connected. Okay, so basically both these windings are connected in parallel, that we have told, and their magnetic axes are displaced by 90-degree electrical. That is the very reason of split phasing. Okay, so both these windings are connected in parallel, but their magnetic axes are displaced by 90-degree electrical. So it is known that when two windings placed 90 degree apart on the stator are excited by two alternating EMF that are 90 degree displaced in time phase, a rotating magnetic field is produced. Okay, so if two windings are spaced 90 degree apart on the stator and are excited by two alternating EMF that are 90 degree displaced in time phase, a rotating magnetic field is produced. If two windings so placed are connected in parallel to a single phase source, the field produced will alternate but will not revolve, since the two windings are equivalent to one single phase winding. So if impedance is connected in series with one of these windings, the currents may be made to differ in time phase and thereby producing a rotating field. Okay, so that's the beauty. So if impedance is connected, okay, say any in series with one of these windings, the currents may be made to differ in time phase and thereby producing a rotating field. And this is the principle of phase splitting. So split phase motors are of following types. What are these? So first one is resistor split phase motors, second one is capacitor split phase motors, and third one is capacitor start and run motors, or it can say two capacitor motors, and another one is capacitor transmotors. So the split phasing is done by this following types, either by resistor split phasing, either by capacitor split phasing, either by capacitor split phasing in starting and then running, and capacitor run motors. Okay, so one after another we'll discuss this split phase motors. Let us before starting this split phasing, I'm once again I'm repeating this starting methods. Basically, starting methods may be either, since main starter winding has no starting inherent starting, so we have to develop starting torque to rotating air gap field at starting must be introduced. So that's why several methods have been developed for the starting of single phase induction motors, and that is classified as split phase starting, series pole starting, repulsion motor starting, reluctant starting. So a single phase motor is which is commonly known by the method of employed for its starting, and the selection of a suitable induction motor and choice of its starting methods depends upon the following. That is, once again I'm telling you the rotor speed characteristics of load from standstill to normal operating speed, then the duty cycle, and third one is starting and running line current limitations as imposed by the supply authorities. Okay, so split phase starting is for induction motor employed. This method is known as the split phase induction motors, and all the split phase motors have two starter windings, main winding or running winding, and another one is the auxiliary or the starting winding, and both these windings are connected in parallel, but their magnetic axis are spaced and displaced by 90 degree electrical. So as when these two windings are spaced 90 degree apart at the starter, are excited by two alternating EMF that are 90 degree displaced in time space, a rotating magnetic field is produced, and if two windings so placed are connected in parallel to a single phase source, the field produced will alternate but will not revolve, since the two windings are equivalent to one single phase windings. So if impedance is connected in series with one of these windings, the current may be made to differ in time phase and thereby producing a rotating field. So this is the principle of phase splitting, and split phase motors, as I told you, they can be say are of following types: say resistor split phase motors, capacitor split phase motors, capacitor start and run motors, and capacitor run motors. So with this split phasing process, we'll start with resistor split phase motors. So this stator of split phase induction motor is provided with an auxiliary or starting winding, say S, in addition to the main or running winding, say M. The starting winding is located 90 degree electrical from the main winding, and operates only during the very brief period when the motor starts up. And the two windings are so designed that the starting winding S has a high resistance and relatively small reactance, and while the main winding M has relatively low resistance and large reactance, and that is shown in the figures I am coming. And consequently, the currents flowing to the two windings have reasonable phase difference, so it is of the order of 25 degree to 30 degree, that is also shown. And this when how it operates now: when two stator windings are energized from single phase supply, the main winding carries the current IM, and while the starting winding carries the current IS. So before coming to that, I am coming to the discussion. So this is actually the main winding or running winding, and this is the starting winding. So they are almost 90 degree phase displacement in such a way, so that this is the starting windings. As I told you in the very discussions of the constructional switch, of the centrifugal switch, which is connected in series with the starting winding, and these two windings are connected, starting winding and main windings are connected in parallel. Okay, and both the windings are being energized from the single phase supply. Okay, so when actually this centrifugal switch, as I told you, that is will be cut off automatically when it is centrifugal switch, when the rotor speed will be at about 70 to 75% of the rated speed, and it will cut off, and then the entire current will flow through this main winding itself. Okay, so I am coming to the discussions here. So that is actually this is 90 degree electrical apart, as shown in this figure. Okay, see this figure. This is actually the single phase motor. This is the stator. This is the stator windings. This is the rotor. Okay, and these stator windings are say divided into two windings connected in parallel, starting winding and main windings. It has characteristics is like this: the starting winding having actually has a high resistance and relatively small reactance, while main winding has a relatively low resistance and large reactance. Okay, so that is also shown in figure B, and considering the current flowing in the two windings have reasonable phase difference, that is 25 degree to 30 degree. That is shown in the diagram also here. This is the starting winding and this is the main winding, and the phase difference is around 25 degree to 20 degree, something like that. Okay, so now actually say since this Operation when two starter windings are energized from a single phase supply. The main winding carries the current IM, while the starting winding carries the current IS. Since the main winding is made highly inductive, while the starting winding highly resistive, the currents IM and IS have a reasonable phase angle, that is of the order of 25 degree to 30 degrees, as I told you, between them, that is shown here. And considering a weak revolving field approximately to that of a two-phase machine is produced, which starts the motor, and the starting torque is given by this say K, IM, IS, and sin phi. So K is a constant whose magnitude depends upon the design of the motor, and when the motor reaches about 75% of the synchronous speed, the centrifugal switch opens the circuit of the starting winding, and the motor then operates as a single phase induction motor, and continues to accelerate till it reaches the normal speed, and the normal speed of the motor is below the synchronous speed and depends upon the load on the motor. So basically, the single phase motor is at the very beginning of the starting. It will start at the two phase motor, and the starting winding or the auxiliary winding will be out of the circuit through say centrifugal switch connected in series with this starting winding, and that is due to when the 75% of the rated speed will be achieved, and these windings are in such a way the main winding is made highly inductive, while the starting winding is highly resistive, and so that the current to main winding and auxiliary winding IM and IS have a reasonable phase angle of difference, phase difference, that is 25 degree to 30 degree between them, and as a result consequently of weak revolving field approximately of two phase machines is produced, and as this speed will be around 75% of the synchronous speed, the centrifugal switch opens and cuts the starting winding from the circuits, and then the motor runs as a single phase induction motor that continues to accelerate till it reaches the normal speed, and the normal speed of the motor is below the synchronous speed, and it depends upon the load on the motor. So everything is shown here. This is the schematic diagram of the resistor split phase motors. This is the reference voltage. This is reference phase. This is starting winding current. This is main winding current. This is of the order of 25 to 30 degrees and this is highly inductive. This is resistive. Okay. So in that way, actually, as I told you, say starting winding is highly resistive, and main winding is highly inductive to achieve this phase angle of 25 degree to 30 degree like that. So that's all about this principal operations, and now we will come to the point of the characteristics. The say torque is 15 to 2 times the full load torque. Made starting torque is 6 to 8 times the full load torque. So this is running torque. So due to their low cost, split phase induction motor are most popular single phase motors in the market, and since the starting winding is made of fine wire, the current density is high and the winding heats up quickly. So if the starting period exceeds 5 seconds, the winding may burn, and unless the motor is produced by built-in thermal relay. So this motor is therefore suitable where starting periods are not frequent. And an important characteristic of these motors is that they are essentially constant speed motors. The speed variation is about 2 to 5% from the load to full load. So this is the torque speed characteristics. This is the full load percentage of torque. This is starting torque. This is at the synchronous speed n equal to ns. This is n equal to g speed. So this is the torque speed characteristics. Now, where it is applicable? So these applications are these motors are suitable where moderate starting torque is required and where starting periods are infrequent. That is to drive fans, washing machines, oil burners, small machines, tools, etc. And the power ratings of Such motors are generally lies between 60 watt to 250 watt. Okay, so we once again I am repeating the entire thing of this resistance start resistor split phase motors. Basically, I'm telling you the stator of a split phase induction motor is provided with an auxiliary or starting winding S in addition to main or running winding M. Starting winding is located 90-degree electrical from the main winding that is shown in this figure. Once again, I'm telling you. Okay, this is the resistor schematic diagram of resistor split phase motors. These phase diagrams. This is torque split characteristics. So let's repeat these things. The starting winding is located 90-degree electrical from the main windings and operates only during the brief period when the motor starts up. Two windings are so designed that the starting winding has high resistance and relatively small reactance, while the main winding has relatively no resistance and large reactance. That's a point to be noted. So since main winding, so during running, this winding is will be inactive. So that's why the resistance that is for IS current loss will be as minimum as possible for the main windings, and that's why the main winding resistance is low. This is another one thing. Another thing is, and starting winding resistance is high, that is highly resistive, and main winding is highly inductive. So that's why that is actually to provide say a phase difference between the two currents, that is starting and the main currents of the order of 25 degree to 30 degree. So this is actually another reason. And when two stator windings are energized from a single phase supply, the main winding carries the current IM while the starting winding current IS. Since main winding is highly inductive and while the starting winding is highly resistive, the currents IM and IS have a reasonable phase angle or phase difference, that is for 25 degree to 30 degree between them, and that is shown in the figure also. And consequently, a weak revolving field approximately to that of a three-phase machine is produced, which starts the motor. And the starting torque is given by this IMIS. Say K is the constant, IMIS assigned. So this magnitude of the constant K depends upon the design of the motor, and when the motor reaches 75 of the synchronous speed, the centrifugal switch opens the circuit of the starting winding, and the motor then operates as a single phase induction motor and continues to accelerate till it reaches the normal speed. So the normal speed of the motor is below the synchronous speed and depends upon the load of the motor. So characteristics, this running torque is 15 to 1.5 to 2 times the full load torque, and the starting current is 6.6 to 8 times the full load current. Due to their low cost, split phase induction motors are most popular single phase motors in the market, since the starting winding is made of fine wire, the current density is high, and the winding heats up quickly. If the starting period exceeds 5 seconds, the winding may burn out unless the motor is protected by built-in thermal relay. This motor is therefore suitable for where starting period are not frequent. An important characteristic of this motor is that they are essentially constant speed motor, and the speed variation is 2 to 5% from normal to full load speed. Okay. Mostly these motors are applicable or suitable for application where moderate starting torque is required and where starting period is infrequent, that is to drive fans, washing machines, oil burners, small machine tools, etc. And the power ratings of such motors generally lies between 60 watt to 50 watts. So with this, we'll conclude this today's discussion. I hope you have enjoyed this session. Thank you very much.